blood flow in artery, or just the airflow inside the very particular room you're sitting in right now? Well, the answer to all of these questions is computational fluid dynamics, or CFD. And so let's just start our journey into this very topic. So, what is CFD? Combination of fluid mechanics, mathematics, and computer science or programming. What you basically do is simulate fluid flow, heat transfer, and other physical phenomena. Instead of like building and testing physically every time, you just simulate, analyze, and improve the designs digitally. Now, how this is important in engineering is, what you get to do is it reduces the need for like physical prototypes and experiments. It helps you reduce cost, design, and it allows you to engineer and like test the multiple designs quickly and efficiently. And the basic result you get, the insight which is the most important, is you are able to get a detailed data on the pressure, velocity, and uh, one.
Guys, let's please give us 5 minutes. We will sort out the again.
Hello guys, am I like audible now? Sorry for the delay.
Um, okay, yeah. Now the PPT is also visible. So basically, I am Tanisi, and before we start, I'll start with a simple question. Like, how do engineers design an airplane or car company sending every design in a wind tunnel? Or how do you simply predict like cyclones, blood flows in your arteries, or the airflow in the very room you're sitting in right now?
Okay. Well, the answer to all of these questions is simply computational fluid dynamics or CFD. So let's start with our journey into today's session. Slide, please.
Okay. So now what is CFD? CFD is basically like a combination of fluid mechanics, mathematics, and computer science or programming. What it does is it basically allows you to simulate fluid flow, heat transfer, or any other physical process in you simulate, you analyze, and you improve your designs digitally. That reduces the need of like physical prototypes and experiments. Because with shifting your entire design digitally, you are reducing your cost, your design time, and it allows you to make multiple designs quickly and efficiently. The basic insight that you get after all this is analysis of your like pressure, velocity, and temperature, like every point of do a physical experiment. Experiment, what happens is you cannot measure all of this all together. You have to take all these parameters separately to get the result, and then you have to like minimize the error that comes.
Am I not audible?
Okay. Next slide, please.
Now let's get into the like applications of CFD in our industry. So in like environmental engineering, CFD is used to simulate like large natural flows like the wind movements, the ocean currents, or the temperature distributions. Using this, you can also like study how the pollutants are spreading in the city, the factory, or industrial areas. Like you, if you want to like find out the pollution spread in a traffic light, or you're trying to find the ventilation that you has to be designed for any building or a tunnel.
So it helps design all these factors safely and environment friendly in a way. So one of the fun fact is like we used CFD during our COVID times to design and study the airflow and virus spread inside the rooms to design better ventilation systems because at that time all we needed is proper ventilation, right? Now, in aerospace industry, it is one of the most important tool in like aircraft and rocket design because we need to use it to like analyze the airflow over wings to improve the lift and the air drag, and we have to study like the turbulence, the shock waves, and combustion in the jet engines. Earlier we what we when we didn't have CFD, what we have had to do was go through wind tunnel experiments, and wind tunnel experiments are like very expensive and time consuming. So with CFD, we are able to do thousands of simulations, which was not really possible before. Now if we move to the like the automotive industry, yeah, if we move to the automotive industry, it is used in like thermal management of the system, like in especially EV vehicles, electric vehicles that are up and upcoming. We use in it to like design the cooling systems for the airflow and the battery cooling and thermal management, because heat management inside electric vehicles is very important. And if we look at overall, it is used in all cars to reduce drag and improve fuel efficiency or vehicle stability at high speeds. And in biomedical engineering, it is used to like simulate blood flow in arteries and veins. And with this, what basically happens is doctors and researchers can understand diseases like blockages or aneurysms, and it also helps them design like medical devices like artificial heart valves, stunts, inhalers, and drug delivery system. So, and as you know, like heart and such, like it's very delicate organs. So instead of testing directly on organs, we are able to do simulations firsthand to improve the safety and performance of the instruments. Next slide, please. Now, let's before we start, we if we are analyzing something, we need to know the factors that they depend on. So basically, fluid flow depends on the fluid physics like the density, viscosity, and compressibility, or the flow regimes like laminar. Is it laminar or is it turbulent? Or the boundary conditions like what are the conditions at the inlet, the outlet, or the walls, and heat transfer to analyze the temperature gradient over the various um, parts of the fluid flow, to which influences like the fluid viscosity. Next slide. Yeah. So now if we look at laminar or turbulent flow,
if you look at the diagrams, we can see that laminar flow is like a smooth flow where the fluid is moving in like parallel layers without mixing. And whereas while you look at turbulent flow, it is very chaotic and it occurs in like eddies and vortices. So the characteristic similarly is that in the like laminar flow, it occurs at low velocity and low Reynolds number, and while in turbulent flow, it occurs at high velocity and high Reynolds number. And now, if we're speaking of Reynolds number, Reynolds number is basically just a representation of the ratio of inertial forces to the viscous forces of the fluid. And the formula for the same is rho Vd by mu, which is rho represents density, V the velocity, and D the diameter, and mu is the viscosity of the fluid. So, while doing CFD simulation, determination of laminar or turbulent flow is very important before performing the simulation. And we do this using the Reynolds number. Like you can see, if the Reynolds number is less than 2300 in pipes, it's laminar flow. And if it is more than 4000, it is a turbulent flow. And if it is between these two numbers, we call it a transient kind of flow, and it's neither nor situation. Next slide. Okay. Now let's take a look at the governing equations. When we talk about using any simulation, there are a number of equations that come into play. The equations that we use during fluid dynamic simulations is the continuity equation, which like represents the conservation of mass principle, where mass entering must be equal to the mass leaving plus the accumulation, and the Navier-Stokes equation, which relates to like the pressure, velocity, and viscous forces, and it is representing the conservation of momentum equation. Other than these two equations, we have our simple conservation of energy equation, that the loss of energy must be equal to gain of energy. These three equations are mainly the main factors that come into play while simulating our fluid dynamics, any equation, situation, whatever we are doing or using it for. The next slide, please. Okay. Now, before you solve any equation, the geometry of your like problem is divided into small cells called the mesh, and the governing equations that we just saw are solved in each of the small cells. Why we do this is basically the smaller mesh size gives us a more accurate result. But to get a more accurate result, of course, the computation time increases. So usually the mesh is made like finer around the walls or obstacles where the velocity or pressure will change. And as like you can even see it in the diagram, like how it is accumulating around the like uh, fluctuations, and otherwise it's like normal. And the second factor is boundary condition, where you defined how the like the fluid is behaving at the boundaries of the domain. Like at the inlet, we usually specify like the velocity or mass flow rate, while at the outlet we specify the pressures, and at the walls we apply the no slip condition, meaning velocity at the wall is zero. And now this is important because wrong boundary conditions will give you the wrong result. And mesh and boundary parameters we basically use to like ensure numerical accuracy, stability, and physical meaningfulness of the simulation operation you are doing. So now next slide. Um, so we saw like all the parameters that we need while doing the simulation. Now, while doing any simulation, you there is an algorithm that comes into a play that
uh, algorithm where you put the values and the result you get. So similarly, solver CFD solver is the algorithm that actually solves the fluid, equations. By converting them into algebraic form and iterating the variables by applying it again and again until like you get a solution that is converging. Now, what is this converging solution? It is basically when a certain number of factors are satisfied. We will look at this later on. But yeah, right now, solver guesses the initial value for like a pressure and velocity and then keeps correcting it until various iterations until the error is very minimal or small. And this whole process is like called iterative solving. Next slide. Yeah. So this is the simulation workflow. In pre-processing, you are defining the geometry, the mesh, and the fluid properties. The result is here, and then we put it for solving in an algorithm, which, like the process described, it iteratively calculates and solves until convergence is reached. And post-processing is the data you get, you visualize it to the results through like streamlines, pressure maps, and data plots, whatever is required. The visualizing part you will see later on in the session. Next slide. Yeah. Uh, Earlier I told like we need to confirm convergence, and what it basically is how do we know if the result is like stable and reliable? And the stable and reliability is called convergence. And to find that, you check the following. You check whether like the residuals is steadily decreasing. What it basically means is residual is like you need to minimize your error. And secondly, you have to see if the value is becoming constant across your iterations. After a point, you have to see if the values are becoming constant and there is no more change. And thirdly, you put like the governing equations you put. So you have to see if the mass and energy are actually balanced and within the acceptable tolerances. If it is all satisfied and solution is showing no meaningful change further with every other iteration, then you call your solution is converged. And if it is not converged, the results are wrong and you cannot report it or use them, and you start your process again. So this is basically how you finally check whether all your indicators together are accepted and converged, and basically your solution is reached or not. So this is the basic workflow of uh, computational fluid dynamics. Now let's move into the MATLAB part and get to know how MATLAB works. Next slide. Sorry, you can stop. Ayush, you can start now.
Hello, is my screen visible? Let me know if my screen is visible.
Yes,
Okay.
it is.
So, hi guys, I'm Ayush, and I will be giving a brief introduction to MATLAB. So, MATLAB basically stands for Matrix Laboratory, and MATLAB is a numerical computing software used by engineers and scientists to perform calculations, simulations, and visualize the results. So, now let us take a look at basic commands. So the first one is CLC, or what it basically does is clears the command window. Next is clear, which clears the variables. And the third one is close all, which closes the figures we have plotted before. So now let us go to the MATLAB platform and take a look at these basic commands. So as you can see, this is my MATLAB window, and I already have a few calculations done in the command window. So when I am starting a new project, I would like a clean slate. So you can just type in CLC and that clears the command window. And as you can see from my previous calculations, I also have a few variables listed here. Now I want all the variables to be gone as I'm starting a new project. Typing clear clears all the variables in the workspace, so you can start afresh. The third basic command is basically close all. As you can see towards the top right, I have already generated a figure. Close all just closes the figure, and so I can maximize the screen for writing the commands. Okay, so those were the basic commands. Now we move on to the variables. So in MATLAB, you can pretty much define variables like any other programming language you may know. And you can also do any mathematical operations, like or just like usual. So let's take a look at few of them. To define any variable, let's say I want to define a is equal to 5, and let's say b is equal to 8. Now I can perform any operation on a and b, and let's say store it in a variable called c. So that will automatically store 40 into the variable c. Now there's another thing you can do if you just quickly need to verify the results and you don't need the results from a into b. You can just do a into b, then that will give you the answer. So MATLAB by default stores any calculation you do in a temporary variable called answer, ans in short. So, but if you need the result of this calculation later, it's better for you to store it in a separate variable. For let's say we do another calculation, let's say 3a plus 4. The new calculation also takes the new temporary variable if you don't save it. So the previous 40, the result is gone. Next, we move on to vectors. So in MATLAB, there are a few different ways you can list out vectors. One is listing each element out separately. Let's say 1, 2, 3, 4, 5 in this case. And the second way is you give the starting value 0, then a colon, then the second parameter tells the increment. So you're incrementing 0.1 from 0, and 10 is the ending value. So it goes like 0, 0.1, 0.2, and so on till 10. Now let us create a few vectors. So 2, 4, 6, and 8. And we will be using these vectors to show the next calculations on MATLAB. We can also define variables in the second way. Let's say y is equal to starts from 0, increments by 0.1, and goes till 5. So that automatically creates all the values. So we don't have to list out every number, and it saves time. Next, we go into matrices. Matrices are pretty much defined the same way as vectors, but in matrices, you put a semicolon to indicate the end of a row and you start the new row. So we can say that A is equal to 1, 2, then semicolon 3, 4. So in MATLAB, even though you're defining it with a semicolon, when you run it, you pretty much see it in a way in which you usually write matrices. So it's pretty easy to see. So after matrices are done, let us look into some mathematical functions that are generally used in any project, and it is good to have a look at them. Square root of x basically works out, gives you the square root of a number. Absolute value just gives you the number without the sign. Sum, sum of x, we'll take a look at how that goes. Sum of x gives you the sum of all the elements, and mean gives you the arithmetic mean of the given values. Max and min give you the maximum and minimum values of the arrays respectively. So again, let's go to the MATLAB window. For the first one, let's say square root of 3. Yeah, it gives us 1.7321. It truncates after 4 points of decimal, which is an expected value. Then next, we also check out absolute. Let's say -3. That gives us the answer 3. And now let's see. Let's say I want the sum of 2, 4, 6. Yeah, now as you can see, just entering the elements like that onto sum does not work. For sum, we need to enter a matrix, not matrix. Basically, we have to input a vector, and that will give us the sum. So 2 plus 4 plus 6 is 12, and mean, max and min also work pretty much the same way. So mean of 2, 4, and 6 give us 4. Max should probably give us 6. Okay. And min of these three elements should give us 2. Okay. So now that's out of the way, we can take a look at our first problem. So let's say we have two, two functions, f of x, which gives us x, and g of x, which gives us x squared. So let's try to find out the area between these two given curves. So here I've already written out the code which will give us the solution, but let's walk through it line by line. So since x and y is the first line, what it basically does is it tells MATLAB that x and y are symbolic variables and not to interpret them as numbers. The next is f is equal to x. F is equal to x is basically telling us the integrand. So we'll be integrating x. And the next is y1 is equal to x and y2 is equal to x squared. These are our two functions. Okay, so now we define a new variable called xlimbs and solve y1 minus y2 x. So what solve basically does is it sees where uh, the functions, the curves y1 and y2 meet, and it gives us the x coordinates of those functions. So then we move on to the fifth line, x1. So xlimbs outputs two values, and if we look at our function x and x squared meet at 2 points, which corresponds to 0 and 1 on the x-axis. So x limbs basically gives us 0 and 1. X limbs 1 and x limbs 2 are basically 0 and 1, and min of that gives us 0. So x1 is basically 0 and x2 gives us 1 because it's the max of these 0 and 1. And now for I, we're integrating. So it is basically a double integral from uh, x squared to x, from limits are x squared to x, and the second one is from 0 to 1. And the MATLAB solves that, and then we plot the graph. So let us plot the graph and see the graph first. As you can see, the blue line indicates x squared, x, and the yellow line from the bottom indicates the x squared curve. And now let us look at a few more interesting lines of code after that. This basically gives us the calculations that we need, but MATLAB has a few more features. So hold on basically says that do not remove the lines we have plotted till now. The blue and the yellow lines are all that is done till this line of code. Now, after, if you look at from the 11th line of code, for I is equal to 0 to, and then we are incrementing for each 0.1 in the x-axis, and we go all the way to 1. It is plotting the green lines from I is equal to I squared. So it plots these green lines for at a distance of 0.1 of the x-axis. And that's basically the end of this code. Now, as you may see, close the figure. If we run this again without the semicolon after the I, it also gives us the value of the area under the curve. Okay. So there are a few more points that we need to keep in mind. Each time we are writing a whole script, we'd have to put a semicolon to ensure that code stops running there. Also, if we don't put the semicolon, we get the output in the command window. Okay. Now let's see some more interesting things. Let's say we have a vector x is equal to 1, 2, 3, 4, and 5. Let's say I want to square each individual element of this vector. So intuitively, I would write something such as this. But let's run it, and then we'll talk through why this is probably not the right approach. Okay, so what x directly squared does is, MATLAB interprets this as x multiplied with x again. So x into x. So this is not possible because we are trying to multiply a 1 cross 5 matrix into a 1 cross 5 matrix again. So how would we actually square each element of the vector itself? So in MATLAB, what we do is we use the syntax x dot exponentiation 2. So that basically exponentiates each and every element of the vector. Same goes for multiplication. If we want to multiply each element of the vector, instead of x into 3, if we want to multiply each element with a number, we do x dot into 3. That multiplies each element instead of the whole vector. Now, let's say at the start of the session, we had seen how to define vectors. So let's revisit that again. X is equal to 0, 0.1, and 10. What this basically did was we had the start and the end point, and we knew how much to increment exactly. But let's say we have the start and the end points, but we need equally spaced points between the 2 points. So in MATLAB, a convenient way to do x is by using linspace. By using linspace, we can generate any number of equally spaced points between these start and end points. Let's say we want to generate 10 equally spaced points between -5 to 5. So yeah, that gives us 10 equally spaced points between -5 to 5. Okay. For our next example, we would need another vector. So let's also create a vector called y using the same command. Okay. Okay. Also, another important feature is zeros. So zeros basically, let's say zeros, the number of rows and the number of columns. That basically generates a zero matrix. So why do we need this? This basically pre-allocates memory for a 5 by 5 result. You can change the number of rows and columns to pre-allocate memory for any number of rows and columns you want. Let's move on to the next important point. Let's say using linspace, we had created linear spaces, so basically 1D vectors, but let's say we wanted a 2D grid. The way so we can basically just combine X and Y to create a 2D grid. In MATLAB, what we do is we use the function mesh grid, and we basically just input the linear vectors we want to make the mesh grid of, and MATLAB basically creates the 2D grid. So now X and Y, this represents the 2D grid. Okay, to further understand how the plotting worked, uh, in our example problem, let's look at some basic plotting. So X goes from 0 to 10 with an increment of 0.1 each, and Y is equal to sine of X. So then we can just, because Y is the dependent variable, we can just plot X and Y. Okay, so this basically gives us a curve. So although this curve looks continuous, it is because we are plotting a single point for every 0.1. So although we can't see it, it looks like a continuous graph. In essence, it is not a continuous graph. Another important feature we need to take in mind is any graph we plot is not really of much importance or use without the labels, and it is best practice to label each graph we make. So let us label this graph. Let's say it's a velocity versus time graph. To label the x-axis, we basically just do x label the label we want to give it under quotes, y label, the x and y label are done, and then we can give a title to the graph. Let's say we call it velocity versus graph, velocity versus time. Okay, so once we run it, we can see that the x-axis has been labeled with time, y with velocity, and we have also given a title to this graph. Another thing we can do is, if we want grid lines on our graph, we can just write grid on, and that will give us grids for the graph. Okay, so it is not necessary that every time we just need one plot. We can have multiple plots together at the same time. So we can have x, we can plot sine of x with respect to x, okay, let's run that. We have sine of x again. Let's say we also want to plot cosine of x. So plot. Now the thing that will happen is, after sine of x is plotted, cosine of x will also be plotted. But the thing is, the cosine of x basically rewrites our graph, and it is replaced by that. So what do we do when we need both the graphs to be displayed one on top of each other? If we write hold on, this basically says MATLAB to not erase the previous graph and keep draw the second graph on top of the other graph. So now when we run it, we can see both the graphs displayed on top of each other. Now that we have two graphs, we also need to label them so that the viewers can easily understand what these curves represent. So how do we represent? So we basically, in order, give a title to each of the plots. So the first plot was sine of x. So we, in the legend, sine of x, sine comes first, and after that we label it cos. Okay, so as you can see, the blue line has been labeled sine, and the other one is cos. Okay, now we move on to the last part. Okay, so how do we plot 3D graphs? So there are three basic methods to do it. One is the contour plots. So what the contour plot does is, it projects 3D data onto a flat 2D plane using lines of constant value. So if we imagine a 3D plane and we have a high slope, the contour lines are much closer to each other. And let's say we have a flat surface, they are equally spaced and much farther apart from each other. Then we have surface plot. Surface plot basically is the solid version of a mesh plot, and it gives you the solid version of any 3D object you're doing. And the third is the mesh plot. Mesh plot is solid plot, but we can just see the skeleton of the plot, so we can see what is there on the other side of it, also on the inside of it. Let us take an example and see all the three 3D visualizations. So again, let's take a mesh grid, x comma y. from 0, incrementing, let's say from -5, incrementing by 0.5 to 5, and z is equal to x squared plus y squared. First, let's do the contour plot. So we can quite simply just do contour x, y, and z. Let's run it. So yeah, as you can see, we get a contour plot, and the 3D graph is basically visualized on a 2D plane. From 0, from x is equal to 0 to minus 1.5 to 1.5, minus 1.5, the spacing is quite large. That way we can visualize that the slope is not that much, but as we go towards 4, the lines are quite closely spaced. That gives us an hint of bigger slopes. Let's see how these differ from mesh plots and surface plots. If we use the same data and we plot a mesh plot, we can see it gives us the 3D visualization, but it is a mesh, and we can clearly see what is opposite to it, and also we can see through it. This is a bit different from the surface plot, because when we run the surface plot, we can see the mesh is filled out by colors, and this gives us a solid figure. Okay guys, so that's it, and I hope you liked the demonstration.
Hi everyone, I'm Gargi and I will be doing a demo for this session. So let's start. So hopefully you guys can see my screen right now. Okay. So let us start by first understanding the problem at hand. I will be simulating the flow of a fluid in a rectangular chamber when it is obstructed by a solid cylinder. So this is like the hello world of the CFD, and it's a very simple simulation, and if you want to follow through this session you can do so. We will be using a GUI on MATLAB called Fear Tool, and it will have multi-physics capabilities on it, which I will be showing you in a bit. Let's first learn a little bit about the problem itself. So the problem states that the solid cylinder that we place inside this fluid chamber is centered at point 2 comma point 2. So in the x-axis it's at point 2 and in the y-axis it's at point 2. Here we will not use any units because in the simulation itself we don't really use them. The diameter of the cylinder is zero point 0.1 and the rectangular channel will be of length 2.2 and height 0.41. We will also discuss that the fluid itself is not as viscous as water is, which is of viscosity around 1, and the viscosity of air, which is around 1 to the power of minus 10 to the power of minus 5. But our fluid will be around the viscosity 0.001. We will also discuss Reynolds number, a little bit of a refresher since Tanisi's presentation, because we will also see that this pressure differences and lift and drag will only be possible in the laminar flow. So, to check that our simulation is correct or not, we will be comparing the results to an already established benchmark, which has three checkpoints: the pressure drop, the drag, and lift coefficients. So, because this is a very common simulation and it has been run for a long time, uh, these benchmark results are standardized and can be used to check if the values are correct or not. So let us learn a little bit more about lift and drag. So as you can see, I have used the example of an airplane here, but we will be simulating a cylinder. So lift here is an opposing force towards the weight, and drag is something that is opposing the direction of motion of the plane here. So, in general, lift is net force on one side of the solid object with fluid flowing around the object, causing the pressure around it to rise from one side and the pressure drop on the other. So, as you can see, the lift is tilted towards one side and it has an angle. This is due to the plane gliding at a glide angle. Uh, And drag here is the force exerted by a fluid in or past an object, and it is applied in the direction of flow. So, as air is flowing towards the plane, the drag is also uh, flowing behind the plane. However, the motion of the plane is forwards, and therefore the drag will oppose the motion of the plane. After we learn about lift and drag, let us also learn a little bit more about Reynolds number and laminar flow. So, Reynolds number, as Tanisi has already said, is inertial force versus viscous force, where inertial force will be represented by the density of the fluid, that's rho, u mean, which is the flow velocity, and d here is the characteristic dimension. So here it's the diameter of the cylinder. And mu, that is the denominator, is the dynamic viscosity of the fluid, which is 0.001, and we get a Reynolds number of 20. So laminar flow is a characteristic by which we measure how the fluid is flowing and what is its characteristic inside uh, with respect to both cohesion and adhesion. So basically, it's how sticky the fluid itself is. Laminar flow is a flow condition in which fluid particles follow smooth and steady streamline with little movement of particle between adjacent layers. So so we will visualize the laminar flow as made out of layers of molecules, one on top of the other, such that there is relatively low movement between these two layers as they hold on to each other. Laminar flow will also cause the inlet flow of the fluid into the rectangular chamber to be parabolic, which we will cover in a little while. So Re equals 20 is a relatively low Reynolds number, whereas the laminar to turbulent flow transition is from it starts from 400. That is, Reynolds number should be around 400 for the flow to be considered in transition period. So that means that the fluid is pretty smoothly flowing in the chamber. Another uh, thing that we need to discuss in modeling laminar flow in CFD is that the mesh that we are using has to have enough resolution that it can accurately capture the velocity profile. And it should also have sufficient accuracy to predict when the flow will transition into turbulent flow. It is also important to know that the rectangular chamber has walls which should have the wall roughness determined uh, previously, and we will also see that the Reynolds number plays a very big role in deciding the how the fluid will flow past the cylinder and also how it will flow inside the rectangular chamber. So let us now discuss boundary and mesh conditions. As we have previously mentioned, uh, there the rectangular chamber will have majorly three parts: the inlet, the body, and the outlet. So the inlet velocity condition is given on the screen, and you can see that the velocity y will be indirectly proportional to h square. And this equation will also give us a parabola at the entrance of the rectangular chamber. You can see it in the first diagram that the inflow is in a parabolic shape due to this uh, factor. If we used a flat velocity, the simulation will spend the first part of the time to basically channel this length artificially into the condition, and it will waste a lot of computational power and thus cause stability issues near the entrance. Let us now discuss the walls of the cylinder. Basically, they will have a no slip condition. That is, the fluid will stick to the walls of the cylinder, and the velocity of the molecules that will stick to the cylinder will obviously be zero. However, the adjacent layer of molecules will have a little bit more velocity than the ones that are sticking to the walls, and this will create a velocity gradient, uh, and thus creating the boundary layer. Because the fluid particles will be stationary at the walls, and uh, it will have a very large velocity in the middle and then curtailing off at the other end of the cylinder. So in our question, we are seeing that the cylinder is not exactly placed symmetrically between the two walls. This will help in causing a lot of drag, but it will still have not a lot of lift because the surface of the cylinder is itself circular, and it does not have any sharp ends or edges like that of an airfoil. An airfoil is the cross section of a plane wing, so there will be a lot of lift due to its teardrop shape, which has a sharper end and a curtailed uh, front part. But because our cylinder example is completely circular, it will have very minimal lift. But as it is not being placed right at the center of the cylinder, it will have a significant amount of drag. Okay, let us also understand the mesh conditions now. So the problem is defined over a closed geometry called the domain, and it is enclosed within a boundary, which is called the boundary conditions. This geometry will be split into small basic shapes called cells. And the collection of all these cells are called meshes. So there can be a lot of different cell types in 2D meshes, which we will see in a bit. We can have quadrilaterals or triangles, or even polygons of more sides if we want to get finer or rougher grids. And in a 3D mesh, these cell types are usually hexahedrals, tetrahedrals, or prisms. Now, for both laminar and turbulent flow, the mesh must have sufficient resolution in the boundary layers to accurately capture the velocity profile, as already mentioned. And there will be a transitioning period where there is a final resolution at which there are critical areas that will be highlighted without it being too computationally heavy on the program. Now let us discuss the results that we will be seeing. So there we will be comparing the pressure drop, which we will see that there is a higher amount of pressure at the front end of the cylinder, and this peters out at the back end of the cylinder, and it's called the wake. We will also see the drag and lift conditions. So there is an equation on the screen where it will take the um, conditions of the lift to drag ratio. As you can see, CL and CD is mentioned. This is the coefficient of lift to the ratio of coefficient of drag. So let us now start with the simulation. Okay. So this is the GUI that I was referring to. This basically makes it very easy to start drawing onto the system without actually requiring a lot of code. So let us first make the rectangular chamber, and then we will define its geometry, which is already given as 2.2 and 0.41. So this is a rectangular chamber, and now let's define the space in which the cylinder will go. The cylinder is centered at point 2 in the x direction and point 2 in the y direction, and it has a radius of 0.05. So that's where the cylinder will be placed. Now we will subtract this area from our gradient so that we can get the place where the cylinder is placed within the fluid, and thus the streamlines will bounce off of this place. Let us now start by defining the grid size. So this is the grid that is already given, and as you can see, it's pretty rough due to the cells being uh, of a size 0.13. So if we reduce the size of the grid or the size of the cell, we can see better results. So as you can see, as the mesh size gets very small, it accurately maps out all of the points around the edges and especially around the cylinder. Let us now define the equations that will help us calculate the velocity and the pressure inside of the chamber. So we already know that the density is 1 and the viscosity is around 0.001. We will now set the boundary conditions. So these boundaries, as you can see, have been labeled as 1 through 8, and these are the representations of both the chamber boundaries and the boundaries of the cylinder. So the upper and the lower walls will have no slip condition. That is, the particles of the fluid will get stuck at uh, the boundaries, the walls, and Let's now map for the outlet, that is the second wall, and that's the outflow. And we can see that the pressure at the outflow is 0. That means this wall is not to be considered. However, we want to see the entirety of the simulation being done in this particular cross section. So that's why the cutoff point is there. However, in physicality, this will be considered as open space. Let us now check the inlet velocity at 4, which will be given like this. So this is the inlet velocity that has been defined previously. Now let us solve this particular equation and with the boundary conditions. So as you can see, there are different pressure conditions and they have been surveyed in the intensity scale like this, where the red portions are where there is the highest amount of pressure, and as we go along, we see that the pressure lowers. Let us now see the contour and pressure lines and the velocity lines. So we will see the contour plot and the arrow plot. Where the velocity field is given, we want pressure, and we only want the arrow plot for the velocity field. So this is where we can see different uh, velocities and different areas in the rectangular chamber. The smaller arrow means that the velocity is lower here, and the larger arrow in the center means that the velocity is higher here. As the uh, arrows diverge around the cylinder, we can see that they are changing course, and as the concentration of arrows increase, it means that there is higher pressure here and here. The black contour lines are also measuring pressure, where pressure increases at the intensity points here and here. As more pressure lines are being generated, it peters out here, this part being called the wake, where the pressure is the lowest. And then as we move through the liquid, we can see that the pressure again stabilizes. Let us now start with the solution part of this demo, where we will start by comparing our results to the results that are already benchmarked. So let's first find the point line evaluation of pressure, where instead of the velocity field, we'll choose pressure at a certain defined point. Now we're taking these points because these points have been already tested, and MATLAB can only configure it to a singular point and cannot take it over a large area. So let's see the answers. So we get a graphical plot like this, but the actual answer we will see is this. 0.121731 and 0.01264668. So this is the pressure at the front and the back of the cylinder. If we take the difference between these two, we will get a difference of 0.109, with and that comparing to the 0.117 of the benchmark reference is pretty accurate. Let us now also see the drag and lift coefficients. So we will use the boundary integration expression here, and we will see that around the cylindrical boundary, which is 5678, uh, velocity is in x direction, and it is being represented by the variable u. So let us change that. We will be using the um, formula that has already been shown in the uh, presentation here, these two formulas, as they are translated into MATLAB. So let us do that. So this is the result of the drag condition, which is to be fine 5.3051. Comparing that to the actual value, that is 5.5795, it is a little uh, under the actual value, but these kind of uh, deflections are to be expected. This can mean that our grid wasn't as fine, or that there is some error in the simulation itself uh, during the processing uh, area. And the drag, as you can see, the drag is pretty high. We will see that the lift condition, which will also be calculated around the same boundary of 5678. So let's do that. This is also the same uh, formula that we have seen in the PPT, just translated into code for MATLAB. And you can see that the lift condition will only give 0.018, which is very low, and that is to be expected as the lift is supposed to be like non-existent for this type of figure. That's the end of the demonstration. If you guys have any doubts, you can ask. Thank you.